We have one more type of nuclear reaction that we're going to look at, and this one is called gamma decay. This is my attempt to draw the Greek symbol for gamma, which is spelled like this. And let's just look at a few. Let's first talk about what this is. So a gamma decay is when a nucleus in an excited state, and I'm going to talk more about that in a moment, but right now let's just write this definition so it's in your notes. A nucleus in an excited state becomes more stable by releasing energy in the form of a high energy gamma ray. So there's a lot in here that we need to unpack. So first of all, let's just clarify some things. Gamma rays have no mass. And that is because they are not particles, they're not strictly particles, they are actually photons. And if you are not already familiar with this concept, photons are light. They are packets of energy, and light does not accumulate the way that other things do, right? Like it's not like if you shine light on a certain spot for a really long time, you're not going to have like light dust there afterwards, and that's because it's really packets of energy. And so gamma rays are a form of electromagnetic radiation, and light is also a form of electromagnetic radiation, the stuff that we see anyway. And so, so are microwaves and so are radio waves. So gamma rays are extremely high energy. They are dangerous to us. They damage they can damage our bodies, and they can go through bones. I mean, it's like really high energy stuff. And so since gamma rays have no mass, once again, we're going to have a situation where our mass number stays the same, just like we had with beta decay. Because in this case, we're not shooting off a particle, we're shooting off a packet of high energy, of lots of energy. So it stays the same. But here's the interesting thing too. This gamma decay is actually the only way that the atom loses that energy or becomes more stable is just by giving off this packet of energy. And so nothing happens to the nuclear particles. So the atomic number stays the same as well. And what does that mean for us? That means that we actually have the same product as we do the reactant. So our nucleus is still the same nucleus. It's just released energy to become more stable. Okay? And then let's just write down a couple different forms of this notation. You might just see the gamma letter, or you might see it shown with a 0 in the atomic number and a 0 in the mass number place. So let's look at an example. Let's say that we have a carbon atom in the excited state. So this is going to be a carbon 12 atom. So I'll draw it with a mass number of 12. And you might see it shown that it's in the excited state by having a little asterisk or star up in the right-hand corner. And so our products of this gamma decay of our carbon atom is going to be that same carbon nucleus plus a gamma ray, plus this big packet of energy. And as we spoke about in the very first video on nuclear chemistry, releasing energy is a feature of nuclear reactions. Nuclear reactions tend to release these a lot of energy, and this is the highest energy type of reaction that we have looked at. So let's draw this for a moment so we can sort of visualize it. Let's start with drawing our 6 protons. 1, 2, 3, 4, 5, 6. We must have 6 because it's a carbon atom. And I'll draw my little plus signs in here. And it's a carbon 12 atom. So we need to have 6 neutrons as well, so that we have a total of 12 nuclear particles, neutrons and protons. 1, 2, 3, 4, 5, 6. Okay, so here's our nucleus, and I'm going to try to show that it's in an excited state by showing it with these sort of motion lines around. Sometimes you see pictures with like a big star in the background, with like, I don't know, like, oh, it's high energy. It has too much energy. It's unstable. Okay, and we're going to show that it becomes more stable. And our more stable form should just be our same nucleus. Let's see if I can save myself a little bit of time by copying and pasting that same nucleus here in a relaxed state. But what we also have is that we have released a gamma ray. And so I'll just sort of maybe show a packet of energy shooting off, okay, into space. And so let's label some of these things. So here is our carbon atom in an excited state. Excited state. And I'm going to put in parentheses, it has too much energy. So it's unstable, it has too much energy. Okay? And then when we look over here, we have our carbon atom in a more relaxed state. Which means that it is more stable. And then here we have, of course, we have our gamma ray. So this right here is our gamma ray. And it is the highest energy waves in our electromagnetic spectrum. And they are very dangerous and can cause cancer, among other things. So this is our visual for our gamma decay. All right. And so let's do one more example here to the side. This is an easy, I hope you can see that this is a very easy reaction to write, because we have the same, if you can write your reactant, then you can write your product. You just have to show that it became relaxed by releasing a gamma ray. So let's do our second example here. So in this example, let's do a word problem. Right, the balanced nuclear equation for the gamma ray, for the gamma decay of, hold on, let's write it correctly, of radium-226. Okay, so once again, let's make sure we understand what the problem's saying. So what it wants is a nuclear equation, right? So we know that it's going to look something like this. And it's saying for the gamma decay of radium-226. So when we see some kind of reaction of radium-226, we know that radium-226 is our reactant. It's our starting material. So let's write that. We know from our previous video that radium has a element symbol of capital Ra. We know that it has an atomic number of 88. And you don't have to memorize this. You could just look at your periodic table and find it in there. The only thing you might have to memorize is that radium has an element symbol of Ra, because some periodic tables do not include the full name of the element. And then we know that it's radium-226. That's the isotope. So our mass number is 226. Okay? And when we're talking about gamma decay, remember that means that we have a nucleus we have an atom that's in an excited state, right? A nucleus in an excited state. And so I'm going to write a little asterisk there to highlight that. And in our reaction, we know that since we're talking about gamma decay, one of our products must be a gamma ray, which one of the ways that we can write it is by writing this. And we also know that we're going to have the same nucleus that we started with, except it'll be in a relaxed state. So I'm just going to write the same thing without my asterisks. So just copy and paste it in this case. And that is it. We have completed this problem. This is all you have to write.